Welcome to Math with Professor V. In this video, we're going to learn about Lagrange multipliers and what's going on behind the scenes that enables us to use this method to find the max or min value of a function subject to a given constraint. Now, most of us, when we learn Lagrange multipliers, we just are given this recipe: set the gradient of your function that you're trying to optimize equal to lambda times the gradient of the constraint or side condition. But why should the gradient of my function equal some constant times the gradient of the constraint? And why will that yield the absolute max or min value of that function? So let's make it visual. Picture a mountain, if you will. And that's your function f of xy outlined right here. It's tracing out or mapping the height of the mountain at any xy point. And the height, let's say, is the value that we're trying to maximize, okay? Now imagine we have a sheet that's slicing through the mountain, just cuts right through. That's our constraint, g of xy equals c. Now this thicker curve right here that I've drawn is basically where the sheet and the mountain meet, and that's the path or the trail that you're allowed to walk on. Now, when you're walking on the trail, right, you can go up a little or down a little on the mountain, but at the very highest point, right, something very special happens when you're at the true max height subject to the constraint. You got to stay on this path. Notice that this contour of f, this level curve of constant height, and the curve of constraint, they kiss, they're tangent. They have the same slope right there. And then here's the key step. We've studied the gradient before, and we know that the gradient always points perpendicular to the level curves of a function. So if this level curve and the constraint curve are tangent here, right? Their tangents are parallel, then their gradients have to also be parallel, which I've highlighted here. See the little gradient. What's happening here at the max? The gradients are parallel. Well, what do we know about parallel vectors? That they're scalar multiples of one another, and that scalar multiple we call lambda. So that's exactly what gradient of f equals lambda times gradient of g is encapsulating. It's not some magic trick, but it's the geometry of what happens when you reach that max height subject to the constraint. I mean, you could go higher, but then you'd be off the path, so then you're not being obedient. And you might have noticed, Professor V, what are those little creatures there on the level curves? Yes, those are little mountain goats. And as my friend Dr. Gupta says, anytime we go hiking, look at the mountain goats. They always go straight up, perpendicular to the contour lines, because they're trying to be as efficient as possible when they traverse the mountain. And you can even see that their poops are perpendicular. It's a funny image, but it does stick because the gradient is the direction of steepest climb, and everything perpendicular to it just moves around you at the same level. So hopefully once you see this picture, parallel curves first, then parallel gradients, the process of Lagrange multipliers should hopefully stop feeling mysterious and just be an inevitable method for solving optimization problems for functions of more than one variable. Okay, I've got 4 lovely examples for you here, a 5th one that's going to be available on my Patreon, and these guided notes are also available on my Patreon, link in the description. Let's just jump right in. So use Lagrange multipliers to find the extreme values of the function subject to the given constraint. So the function that we're trying to optimize, f of xy equals x times y, and then here's the constraint, 4x squared plus y squared equals 8. Now this constant on the right-hand side is really irrelevant. You could think of g of xy equals 4x squared plus y squared minus 8, but notice when I take the gradient of g, that minus 8 plays no role. So I don't usually even take the time to rewrite it like this because it's pointless. Okay, so let's start off. Gradient of f equals lambda times the gradient of g. What's the gradient of f? So partial derivative of my function with respect to x will be y, and then next component would be x, and I have that equals lambda times 8x to y. Now we're going to set up a system of equations. So how many unknowns do we have? We have 3, y, x, and lambda. That means I need 3 equations. So start off by equating the first components with each other. So that would mean y is equal to 8 lambda x. Second equation comes from equating the y components together. So that would be x equals 2 lambda y. And if we have 3 unknowns, we need 3 equations. Where's the third one? It's the constraint equation. So 4x squared plus y squared equals 8. Good? Okay, now from here is where students have the most difficult time because every single one of these systems is different. They're not linear systems, as you're noticing most of the time, and the process in which you have to tackle solving them can vary. All right, so I'm going to start off isolating lambda in the first 2 equations. You have to sometimes play around with them, okay? It's just practice and pattern recognition, and sometimes you can have more than one approach. That's totally fine. So from the first equation, lambda equals y over 8x. From the second, lambda equals x over 2y. And so if I set those equal to each other, right, because they're both equal to lambda, I get y over 8x equals x over 2y. If we cross multiply, we get 2y squared equals 8x squared. So y squared is 4x squared. And I'm going to stop there and substitute this into equation 3. So then now we have 4x squared plus 4x squared equals 8. So 8x squared is 8. X squared is 1, which means x equals plus or minus 1. So if x is plus or minus 1, that means y squared is 4. Y could be plus or minus 2. And either of these values of x can be paired with either of these values for y. So we have 4 ordered pairs that comprise our solutions. So let's see. We've got 1, 2, 1, negative 2, negative 1, 2, and negative 1, negative 2. So from here, how do we determine which yields our absolute max, which yields our absolute min? Well, you got to go back and substitute them into the function that you're trying to optimize. In this case, f of xy was x times y, right? So evaluate the function at each of these 4 points, and let's see what we get. So we're just multiplying them. Look how relaxing. 2, negative 2, negative 2, 2. Perfect. So the smallest values, these are where my function attains its absolute min value. The absolute min value would be the z value, f of xy. Where it occurs is the ordered pair, 1, negative 2, or negative 1, 2. And then the positive 2's are my absolute max values. So the method of Lagrange multipliers will yield both. If I drew a valley on my mountain in that original picture, the method would work as well. So if we go back, I mean, here, I'm for crying out loud, that looks almost like the min, right? And again, let me draw it better. Coming up here, their tangents are equal, the gradient's pointing that way. Again, they're scalar multiples, okay? So you can get both the absolute max and the absolute min when you apply the method of Lagrange multipliers. So efficient, right? So beautiful. Okay, good. I would say this is all your answer. You know what's most important? Check with your instructor how they want you to format your final answer. Do they want everything written out like this? Do they want a table? Just check with them. Everyone's different, so just make them happy. Okay, let's look at another example. Here's our function, and then we have 2 constraint equations. Oh me, oh my. So what do? It's not a big deal. We're just going to have to add in another constant, right, for this second constraint. So after lambda, we usually use mu. That's just the way we typically set it up. So we'll set this one up as gradient of f equals lambda times the gradient of g plus mu times the gradient, I'll call that guy h. So this is g of x, y, z, and this is h of x, y, z. So this time we'll have 3 components. How exciting. Okay, gradient of f, look how cute. 1, 1, 1 equals lambda times 2x, 0, 2z plus mu times 1, 1, 0. Good? Okay, perfect. Now this time we have 4 unknowns, x, y, z. Oh no, I lied, 5. X, y, z, lambda, mu. So we need 5 equations to solve the system. So we'll have 1 equals, I'm setting the x components all equal to each other, 2 lambda x plus mu. Second equation, 1 equals mu. Ooh, that's good. 3, 1 equals 2 lambda z. That's it. And then equations 4 and 5 are the constraint equations, or side conditions, some people call them. Okay, where to begin? Well, I'm very excited. I know mu is 1, right? Okay, so let's put that back into first equation. So that means 1 equals 2 lambda x plus 1. So that means lambda times x is 0. Using our zero product property, then either lambda is 0 or x is 0. So let's explore either of those cases. If lambda is 0, and I plug that or substitute 0 in for lambda into equation 3, which is sitting right here, I would get 1 equals 2 times 0 times z. I get 1 equals 0. Is that true? No, that's a contradiction. So what does that tell me? It's not possible for lambda to equal 0. Throw that out. Okay, now what if x is 0? Where should we go? You could go to 4 or to 5. Let me go to 4 first. If x is 0 into 4, I get z squared is 2. So z equals plus or minus rad 2. And then into 5, then I get y is 1. Okay, perfect. So in this case, I'll have 2 ordered triples because x is 0. With that, z could be either of these, and then y is set at 1. So you'll have 0, 1, rad 2, and then 0, 1, negative rad 2. Evaluate the function. What was our function? It was x plus y plus z. So f of 0, 1, rad 2 would be 1 plus rad 2. And then the function evaluated at the other point would be 1 minus rad 2. So clearly this will be our absolute max. And this is our absolute min. Okay. Perfect. Hopefully that was fun. Let me box this guy up. Okay. Let's look at another example. F of xyz equals yz plus xy. Again, 2 constraints. Xy equals 1, y squared plus z squared equals 1. You know what I think? I think you should pause the video, try this on your own. See how you do. So we have 2 constraints. So we'll do gradient of f equals lambda gradient of g plus mu gradient of h. So we'll have y plus x plus z, and then y equals lambda times y x 0 plus mu times 0 2y 2z. Again, 5 unknowns, 5 equations. So first one's going to be y equals lambda y. Yeah. Second one is x plus z equals lambda x plus 2 mu y. Third one is y equals 2 mu z. 4 is xy equals 1. 5 is y squared plus z squared is 1. Okay, where to start? Sometimes you just got to go for it. Let me start with number 1. It has like the least amount of variables, least amount of craziness going on. So we have y, if I move everything to the left, y minus lambda times y is 0. Factor out a y, and then we can use the zero product property. So either y is 0 or lambda is 1. Okay, then you explore each of these possibilities. For example, into equation 4, which tells me x times y is 1, that would result in x times 0 being 1. But 0 cannot be 1. That is a contradiction. So this is not happening. Y is not 0. Can lambda equal 1? Scan, scan. I don't see lambda here. No lambda, no lambda. I got this from the first equation, so now I need to see what happens if I substitute it into the second equation. Okay, so into 2, x plus z equals, if lambda's 1, I'd have x plus 2 mu y. These cancel. Okay, I'm liking this. And then I have a z, I have a mu and a y. And this is from equation 2. And then look, I've got a z and a mu and a y there. So let me solve for mu in what I have here and 3, and I can set it equal to each other. Meaning, I'm going to say mu is equal to z divided by 2y. And then from 3, do you see this? And from 3, mu is equal to y over 2z. So then I could set both these quantities equal to each other. Y over 2z equals z over 2y. Cross multiply your little heart out and you'll get y squared equals z squared. Yes, I canceled the 2's already. We got to get this show on the road. So then y equals plus or minus z. You could say z equals plus or minus y. It doesn't matter. Now where do we go? Right here to 5 because it only involves y's and z's. Perfect. Look at all these crazy arrows. Okay, into 5. Z squared plus z squared is 1. So 2z squared is 1. Do you cross your z's? I hope you do. So z squared is a half, which means z equals plus or minus 1 over rad 2. Okay, now here's the thing. Y equals plus or minus z. So y is also going to be plus or minus 1 over rad 2. But already this is giving me like 4 different options, right? Because y could have the same sign as z or it can have the opposite sign as z. Okay, now you see how x times y equals 1 from equation 4? Okay, x and y have to have the same sign because they equal positive 1. Their product is positive 1. So if x is negative, y has to be negative. Or if x is positive, y has to be positive for their product to be a positive number. So that means x is going to be plus or minus rad 2. It has to have the same sign as y. But y does not have to have the same sign as z. Oh my God. So we have so many ordered triples. And yes, there is a clean way of writing them out so you don't lose your mind. Are you ready for it? Okay. So x could be plus or minus rad 2. Y could be plus or minus 1 over rad 2, but they have to agree. Like if x is positive, y is positive. Or if x is negative, y is negative. Like that. And then z could be also matching the same signs, plus or minus 1 over rad 2. Also, x could be plus or minus rad 2. Y has to have the same sign, but z could have the opposite sign as y. Z could be minus plus 1 over rad 2. This is legitimate notation, okay? That way I'm not sitting there writing out, oh my God, so many ordered triples, I would lose my mind. So let's see, which is going to give me the absolute max, which is going to give me the absolute min. We got to plug into the original function to see. I did it for you already. Aren't you so excited? This is 3/2, and this is only 1/2. So this is our absolute max, and this is our absolute min. Ooh, that was good. I kind of love it. Oh no, whatever. We'll just leave it. I'm like thinking, because my class is taking their exam next week on Lagrange. Well, on this whole unit. Like, is this a good problem for the test? Perhaps it is. Okay. Last one for this video. We can obviously apply the method of Lagrange multipliers when solving some of the applications that maybe you've looked at in previous lessons. Okay, here we go. So find the points on the cone, z squared equals x squared plus y squared, that are the closest, so sorry, to the point 420. So this time we have to come up with the function. Oh my goodness, we can do it, don't worry. Okay, Closest means we're optimizing or minimizing distance, yes. And we know the distance formula from some arbitrary ordered triple to this given point. So how would you use the method of Lagrange multipliers? Well, the function that you're going to optimize is distance. I'm going to do distance squared. That way it's easier to find the gradient and I won't have to use the chain rule so much with the square root. Do you see what I'm saying? So I'm setting up distance formula from arbitrary ordered triple, arbitrary xyz, to the point 420. And then what would my constraint be? My constraint is that this ordered triple must be on the cone. So such that z squared equals x squared plus y squared. So this is my g. I'm just going to say x squared plus y squared minus z squared is g of x, y, z. So I'm minimizing the distance from some arbitrary ordered triple in 3 space to this point. And then instead of this being anywhere and everywhere, I'm restricting it to being on the cone. Okay? So fun. So then we have gradient of f equals lambda times the gradient of g. And then, yes, aren't you so glad that I'm using distance squared? Whatever point minimizes the distance, whatever order triple, it will also minimize the distance squared. I'm just going to have a much more relaxing time finding the gradient using distance squared. So we'll have 2 times x minus 4, 2 times y minus 2, and 2z equals lambda times 2x, 2y, negative 2z. We have 4 unknowns, so 4 equations. Equation 1, x minus 4 equals lambda x. Equation 2, y minus 2 equals lambda y. Equation 3, z equals negative lambda z. I'm getting rid of the 2's already, people. 4, constraint equation, x squared plus y squared equals z squared. Okay. Let us see. What's calling out to me is equation 3 because it looks the simplest. You see that? And I have z plus lambda z is 0. Factor out of z times 1 plus lambda is 0. So 2 things can be true. Both could even be true. Who knows? Z could be 0 or lambda could be negative 1. Let's explore both options. What if z is 0? Let's go into equation 4. That's the only other place I see z. That would tell me x squared plus y squared is 0. That's only going to be true if x and y are both 0, right? There's no other way for that to be true. But this is a problem. This is a contradiction. Why do I say that? Because look at equation 1. If x is 0, does 0 minus 4 equal lambda times 0? Does negative 4 equal 0? No. Look at equation 2. If y is 0, problem, 0 minus 2, does that equal lambda times 0? Does negative 2 equal 0? No. Contradiction. So what does that mean? This is not possible. Don't feel badly when this happens. This means you're getting good info. We're getting somewhere. What does this mean? It means lambda's negative 1. Hooray. So from there, I can go get x and y, can't I? Yes. Okay. So x minus 4 equals negative 1 times x. Perfect. So 2x equals 4. X is 2. Cute. And then that's from equation 1. And then from equation 2, y minus 2 equals negative 1 times y. 2y is 2. So y is 1. Yes? Perfect. And then how do I get z? Right here. X squared plus y squared is z squared. So we'll have 2 squared plus 1 squared is z squared. So z equals plus or minus rad 5. So we actually get 2 points. The problem said find the points. So the points are 2, 1, plus or minus rad 5. And you might say, why are there 2 points? Well, remember, we have a cone. want to like draw a nice one, you guys, but I'm just freestyling. We have a cone, yes. Yes, and we want to find the points on the cone that are the closest to 4, 2, 0. Well, will there not be 2? 1 here, 1 here. And they have the same x and y coordinates, just different z coordinates? Yes, yes. Hopefully that makes sense. Okay, I have one more example, but I'm going to solve it on my Patreon. Find the maximum volume of a rectangular box that is inscribed in a sphere of radius r. These guided notes are going to be there too. And that concludes the lesson. I hope you found it helpful. Imagine the mountain, imagine the trail, imagine the mountain goats and their perpendicular poops, and hopefully the idea of Lagrange multipliers makes a little bit more sense and it doesn't feel like just some random setup that works and you have to just take everybody's word for it. We don't like doing math that way. Absolutely not.